All right, so we're going to talk about the electrons and the electron configurations. So we did this really quickly in class. If you feel okay understanding the s, p, d, and f orbitals, you can go ahead and fast forward to actually some of the practice problems, or you can go ahead and watch this and see how you're doing. Okay, we're going to do a couple things at once. We're going to locate where these things are on the periodic table, and we're going to look at what these orbitals mean. So the next slide here. These are s orbitals, and what an s orbital is, it stands for sphere. Okay, so these are the probable locations that the electrons are going to hang out. And so the first energy level, or the first quantum, okay, we call that n. N equals the principal quantum energy level. So up until this year, when you used to do your electrons like this was your first quantum, your first energy level, and this was your second one. Okay, so you've done these, you just never knew that they were called the quantum or principal energy level, or n. Okay, so in this first energy level, this first quantum, or n1, we have what's called an s orbital. And there's only one orbital, and it can hold 2 electrons. So here's a picture of that. So you have the s orbital, and 2 electrons can hang out in this region. The second quantum, or the second principal energy level, also has an s orbital, and you can have electrons hanging out here, and the third, and so on and so on. Okay, so your s orbital is going to hold 2 electrons. All right, so there's your s orbital. All right, let's go to the next slide. After the s orbital, we have what's called the p orbital. Okay, all right, so the p orbital doesn't show up until the second principal energy level, or second quantum, so the second ring. All right, and the p orbital, there's 3 of them. There's 1, 2, and 3, and these are the locations that 2 electrons each could hang out. Okay, so in these 3 orbitals, we could hold a total of 6 electrons, and this is what it looks like when it's all mushed together. Okay, so here's all the 3 p orbitals coming together. Okay, so what does this mean? I'm going to go back to the very first slide. All right, take my highlighter here. The first 2 families on the periodic table, remember families go up and down, and helium counts, are what we call the s orbitals. All right, so quantum number 1, principal energy number 1, has an s orbital, which can hold 2 electrons. That's it. So here's the s orbital, 1, 2. Here's the s orbital, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So all of these are the s orbitals. Okay, so just like you've been told in the past, or the first ring, the first quantum energy level, can hold 2 electrons, and we can see now it's because there's just an s orbital holding 2. Okay, the second principal energy level, or second quantum, still has an s, right? We've got s's right here. That can hold 2 electrons. But now we have a new set of orbitals. So remember what we just saw on that other slide. You have 3 p orbitals. These guys are right here. These are the p orbitals. All right, if there are 3 p orbitals, that means it can hold a total of 6 electrons. So 1, 2, 3, 4, 5, and 6. So the second energy level can hold a total of 8 electrons, because 2 can be in the s and 6 can be in the p, and that gives us 8 total. All right, so the third quantum, all right, we've got an s, holds 2. You have a p, holds 6. But we know that we've been told that it should have 18. So we're going to go ahead and go a couple slides ahead here and go right here. These are called the d orbitals. The d, hold on. Edit. Okay. The d orbitals don't show up until the third quantum, okay, the third energy level. And there's 5 of them. 1, 2, 3, 4, 5. Crazy shaped. What that means is 2 electrons can hang out in this shaded region. They can move all over in this region. And 2 can hang out here, and 2 here, and 2 in here. All right, so there's 5 orbits, 5 orbitals that hold 2 electrons each. So 1, 2, 3, 4, 5, and each of them hold 2. So we can hold a total of 10 electrons in the d orbital. All right, well, let's go back to the very first slide then and see where these guys show up on our periodic table. Right here. Okay, so the transition metals are going to be our d orbitals. So in the third quantum, we have S, P, and now all of a sudden we have D, which can hold a total of 10 electrons, giving us 18 total. Okay? All right, here's the issue though. Notice that in the third energy level, the D group's not there. Okay? It doesn't start until down here. We know this has to be 3D because we just said that. That makes this 4D, 5D, and 6D. Here's what happens. Just like we talked in class, it takes less energy to go ahead and go out to that fourth quantum or that fourth energy level. So 1, 2, 3. Instead of continuing filling up this third ring, we can actually jump ahead to the fourth one and fill up the s orbital. Okay, it takes less energy to do that. The example we used in class, we talked about if you're standing in line at the grocery store and all of a sudden there's available checker for just a couple people, you're going to go ahead and go. You're not going to wait in line and keep going here. You're going to jump ahead to that line that just opened, and then if it's full, everybody files back into where they're supposed to. Okay? All right, so what this means for us is on our periodic table, these are the Ds, but this group is behind by 1. All right, so we have 4, but the D's are going to be 3, and 4, and 5, and 6. I would physically write that on your table. It takes more energy to try to fill this, so he's going to come after the 4s. Okay? All right, let's move on to the fourth energy level, the fourth quantum. You know there should be 32 total electrons. All right, well, S is going to hold 2. P is going to hold 6. We now know that D holds 10. That gives us 18, so we're looking for 14 of them. All right, well, let's go to our last slide here and see what we have. We have the f orbitals. And in the f orbitals, there are 7. There are 7 different possibilities for where those electrons can hang out. 1, 2, 3, 4, 5, 6, and 7. 7 different orbitals, okay? If each one of these can hold 2 electrons, somewhere in these shaded regions, we get a total of 14 electrons can be housed in the f orbitals. All right, going back to our very first slide here. Almost there. Okay. Down here is where you're going to find your F's. Okay, so these guys down here are now the f orbitals. All right, we know that 4 is the first time that the f orbital should show up. And that gives us 32 electrons here. But there's 14 electrons. That's a lot of electrons to try to fit in that small area. So the thing is these guys actually are 2 behind. What that means is it takes more energy to fill these guys, to fill this up, than it is to go ahead and jump ahead. All right, we can actually jump out to another quantum energy level before coming back and filling this up. So this is 4F, and this is 5F. Okay, so you're going to read your periodic table like you're reading a book. So I'm going to try to erase a little bit of this down here. See if I can do that without causing too much of a trouble. Nope. All right, try just that bit. All right, so here's what we're going to do. Eee, went too far. Ah, okay, I'm done playing. Thought I could get there, sorry. Okay. So slide it. All right, try to go back. There we go. All right, back to the pen. All right, let's look at gallium. So gallium's right here. He's got 31. So I'm just going to put gallium right here. All right, how do I get to gallium? I'm going to go through 1s, 2, because I went through the first quantum, through the s orbitals, and there's 2 of them. I'm going to go to the second quantum, going through the S, and there's 2 of them. I'm going to go through 2p. There's 6. 3s2, right here. 3p, 6. 4s2. Okay, remember my D's are behind by 1, so I'm going to actually go 3D, and I'm going to go through 10 of them. Now I'm back to the P's, so this is back to 4p, 4p, 1. Okay, so here's gallium's electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. That is the ground state configuration. That means without those electrons being excited, where are they at? Where's their location? Where are they filling? Okay, so that's every place that they should be filling. Okay, let's go ahead and go down to one of these with the F. Okay, so we're going to go to iridium. And you're like, well, I thought you wanted an F. Here's what I mean. Okay, so here's iridium, 77. So I'm going to go ahead and write it right here. I'm going to go a little bit faster. So to get there, we want 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. All right, we're right here. I got to go through this. So I'm going to go 3d10, back to 4p, 4p6, 5s2, right here. 4d10, 4d10, 5p6. All right, we are at 6s right here, 6s2. All right, now look, 55, 56, I have to jump down. 55, 56, 57, I have to actually fill up 4f first, all 14 of them. Now once 4f is filled up, I can now come back. I am in 5d, and I'm at 1, 2, 3, 4, 5, 6, 7. 5d7. That is the ground state electron configuration for iridium. All right, this was kind of an intro to give you the background knowledge on where the s, p, d, and f orbitals are on your table, how many each level can hold. The next video will give you some more of the examples and noble gas configurations.